Welcome back to Introduction to Machine Learning, CS 480-680, as taught at the University of Waterloo in fall 2024. This is lecture 10 in the series, and today we're going to be talking about decision trees. So a bit of some motivation before we get into the technical details. So when human life is on the line, like is the situation. We have autonomous vehicles navigating, complex situation like an intersection. We really need to have an interpretable model. So in the context of this image here, let's imagine a self-driving car that following another vehicle at an intersection. So it needs to make split-second decisions about whether to do things like brake or accelerate or change lanes. And if the model makes an unexpected or unsafe decision, it's absolutely essential to be able to explain why it made that choice. And so rule-based decision making can offer transparency by ensuring that the vehicle, it adheres to well-defined safety protocols like, maintaining a minimum safe distance or recognizing when the car in front has stopped. And so in situations like this, a highly accurate but black box, opaque model, it might achieve great performance in ideal conditions, but it could struggle to generalize safely in rare critical situations. Maybe if a pedestrian suddenly crossed the road, what might it do in that situation? And in an interpretable model, on the other hand, then engineers have the ability to understand and validate every decision the car might make. So this would ensure that the vehicle behaves as expected in every situation, which would reduce the risk of accidents and ultimately, protect lives. So yeah, as I mentioned today, we're talking about decision trees, and these are a class of hypotheses characterized by kind of recursive partitioning of the state space, and they provide a framework. These decision trees provide a framework for learning these kind of rule-based decisions. So in the context of this vehicle at an intersection, let's see how such a model can be used to make transparent and interpretable decisions. So the idea is that the problem gets broken down into a series of binary decisions, such as whether the traffic light is red or if it's green, and then whether the distance to the vehicle is less than some amount, say 20 meters. So this tree captures different driving scenarios and the corresponding actions, like braking, or whether to keep going, to proceed. So within this decision tree structure, each decision node in the tree represents a question that splits the input space into two regions in this case. And so then as you move down the tree, the model refines its decision based on these rules. So it results in specific actions at the end nodes here. So if the traffic light is red, the decision is automatically to brake, regardless of any other factors. And if it's green, the model then considers more nuanced information, like if the distance to the vehicle ahead to decide whether to proceed or brake. So the idea is that we're doing this step-by-step partitioning process to learn a simple yet really powerful set of rules for safe driving behavior. Decision trees have a very natural terminology to describe their structure. So conveniently, the root is the starting point of the tree, and this is where the initial decision is based on a specific feature or question, and then it branches into different paths. And then the intermediate points along along that path are called nodes, and they each represent a subsequent decision or test that further splits the data into smaller groups. And then finally, we have the leaves at the end of each path. indicated by the diamonds here. Oh, sorry. So that's the root. And then these are the leaves at the end. So these leaves represent the final outcomes or predictions based on the series of decisions that got made along the way. So we can tie this back to the kinds of models that we're used to seeing in this course. So we can visualize the behavior decision tree based on the features of the features in the nodes. So in this case of a decision tree for the vehicle at the intersection, the two key features are the state of the traffic light, which was red or green, and the following distance from the car ahead, which was a continuous value actually. And so we can put these features, traffic light state and distance, as the axes of a 2D plot. So something like that. And then in the case of the traffic light state, that's a binary variable, so that would only take on values of red or green. So the tree starts off by checking the traffic light state at the root node. And then if it's red, the vehicle should brake, regardless of the distance. So that's, this decision is represented by the left branch leading directly to the brake leaf. So we automatically know for this entire region of state space, the decision is to brake. And so, we would, for this entire region of state space here, when the traffic light state is red, the decision is automatically to brake. And then if the light is green, the tree moves to another node that looks at the distance. So now if the distance is less than 20 meters, it's not safe to proceed because the car ahead is pretty close to it. So the decision is to brake. If on the other hand, the decision, the distance is 20 meters or more, the car can safely move forward. So the decision is to proceed. So this would correspond to partitioning the subspace corresponding to a traffic light state of green. If the following distance is less than 20 meters, then we're braking. If it's 20 meters or more, then we're proceeding. The key thing is that the entire space is divided into regions corresponding to different decisions that the tree makes. And so this is why we can make this claim about interpretability and reliable decision making, because we know exactly what this model is going to do, regardless of where it is in the space. Final comment: so the decision tree creates these boundaries and feature space based on the learned rules, each step in the decision tree carves up this space, makes decisions that are easy to both interpret as well as visualize. Another interesting thing about decision trees is they're learning nonlinear decision boundaries using these kind of axis-aligned or compositions of axis-aligned rectangles. We can see in this left plot here how the decision tree splits the feature space into these neat rectangular region. And then each dashed line represents a decision boundary created by a question about one of the feature, either feature one or feature two. This allows the tree to separate the data into different classes using simple interpretable rules that are very easy to understand. We can compare this to a linear model. We've seen many examples of this throughout the course, a linear model is constrained to a right line, to a simple decision boundary, simple line that would try its best to separate the classes. This is a decision boundary here is a linear combination of feature one and feature two. And we can see that this is less flexible. It can't capture the complex relationships as well as the decision tree. You could use nonlinear feature maps to transform the input features into some higher dimensional space or some other feature space to create more flexible decision boundaries using a linear model. But then you would lose the interpretability that comes from working directly with the original features that have a direct physical interpretation in terms of the state of the car and its surrounding environment. So yeah, decision trees can approximate nonlinear functions, or at least certain nonlinear functions, but still make decisions that are easy to understand. So in terms of how decision trees make predictions, it's based on the majority class within a region. So once a decision tree has split the feature space into different regions, like the rectangular regions that we saw in the last slide and copied over again here, the prediction for any one point that falls within one of these regions is determined by the most frequent class in that region. So for instance, this highlighted or this gray subregion RM, the decision tree would count the number of blue and orange points, and whichever class has more points in the subregion would be assigned as the predicted label for any new point that falls within the region. So this new test point here, that black one, that would get assigned a blue label because that's the majority class within this region. So rigorously stated, the label YI is assigned, the label assigned to an observation is determined by looking at the empirical fraction of observations within each class label, with each class label in that region. And so that this is this empirical fraction PMK. So then we compute the empirical fraction for each class K, and then YI is assigned to the K that maximizes the empirical fraction. The empirical fraction in turn is the fraction of the number of data points in the region R sub m that have class K, divided by the total number of observations in that region. So basically, we find out the observation for every feature vector xi that lives within some region Rm. We then add up find out the number of observations that have class K, so where yi is equal to k, and then we divide by the total number of samples in that region, and so that's our empirical fraction p and k for a class K. So pretty straightforward. We're assigning labels assigning the label for a new test point as the majority class within a particular subregion. Okay, so that's how we make predictions for new points, but we haven't actually yet talked about how we learn a tree. So when we can talk about building a decision tree, so they are built, and it's actually something that we grow step by step. It starts with the entire data set. So the idea is that we start with the entire data set, and then we gradually split it into smaller and smaller regions as we add decision nodes. And so our goal at each step is to decide which feature to split on, and then where to place that split in order to best separate the data. So this is determined by choosing the feature and a threshold that minimizes a certain loss function, which measures how well the data points are grouped in the resulting regions. Okay, so let's imagine we have a training data set, S, with observations and their labels. So the aim is to find the feature with the feature index, we'll denote that as J hat, and the threshold T hat that produces the best split. So this best split in term is one that minimizes the loss S, which we'll get into next, after dividing the data into two disjoint subsets, S0 and S1. So the loss is computed as the sum of losses for S0 and S1, weighted by the sizes of these subsets. So in other words, we want to reduce the impurity within the resulting regions as much as possible. Right, so the math here shows how we achieve that. So we consider each feature index J and each potential threshold T, and we split the data set S into two groups. S0 contains all the points where the value of feature J is less than or equal to T, and S1 contains the rest. And then we then calculate the loss for this split configuration. And then the goal is to find the combination of J and T that results in the smallest overall loss, effectively finding the best way to separate the data at that step. And so that's just one step. But then this process is repeated recursively. So we grow the tree node by node until some stopping criteria is met that we'll get into at the end of this presentation. So to learn a decision tree, we need to define that loss function that tells us how good or bad each split is. One straightforward option is the misclassification error, and this measures how well or how often the model's predicted labels differ from the true labels. So the misclassification error is simply the fraction of points within a region. So the fraction of points within a region where the predicted label does not match the actual label. So in other words, it's a way of capturing how many mistakes we're making within that specific region. Right, so to calculate the misclassification error for a region S sub M, we take the sum of incorrect predictions and divide that by the total number of points in the region. So we can also write this in terms of the majority class in the region. If we assign the majority class labels to all points in the region, then the misclassification error is just 1 minus the fraction of points that belong to that majority class. So the more homogeneous the region, in essence, the more points having the same label, the lower that misclassification error is going to be. To get some intuition here, let's consider a couple examples. Let's say let's consider the case where for a particular region you were predicting all zeros, and then all the true labels within that region is also 0. So this would correspond to perfect prediction. So the empirical fraction is 1, and then 0 loss. On the other hand, if we were, we would be predicting all 0 labels within a given region, but then perhaps a couple have the opposite class. In this case, the empirical fraction would be 0.5, and therefore our loss would be 0.5. So we'd have a 50% misclassification error. This one here would tell us that the split isn't doing a very good job of separating the classes, and we should probably consider some other feature or perhaps some other thresholds to be able to improve what's going on here. Misclassification error is a simple and intuitive loss function. It has a couple limitations. So it doesn't consider, it's not very sensitive to how close a split is to being good. So it's not very sensitive to changes when the majority class is already dominant. And so because of this, there's a couple other loss functions that are considered, specifically entropy as well as the Gini index, and they're defined here. So entropy is defined as the product of the empirical fraction times the log of the empirical fraction, summed over the k classes, um, and then we report the negative of that amount. So this measures the amount of uncertainty or disorder within a region, and this is going to be highest when the classes are evenly mixed, which means that the split hasn't done a good job of separating the classes. As the region becomes more homogeneous, we see more and more points of the same class. The entropy decreases, so that would indicate a better split. Gini index is uh, defined similarly. Defined similarly. The elements of statistical learning text compares these three measures for different values of the empirical fraction p. So we can see that all three curves have some similarities, reflecting how well a split separates the classes based on the probability, uh, based on the empirical fraction p of observing a given class. And so they're all measures of impurity. So you'll notice, but the misclassification error has a bit of a different shape. So it's not going to be differentiable, for example, at p is equal to 0.5. And we can see that the gradient with respect to p when any one class dominates is less than it is for the Gini index and the entropy. So when one particular class dominates, Gini and entropy are more sensitive to those changes. Um, and yeah, Gini index and entropy are smoother and differentiable, so they're more amenable to numerical optimization. Um, but yeah, so yeah, different shapes of loss functions, but there's three different loss functions that you could choose for your decision tree. Yeah, one final thing to note is that in this figure, the value for entropy, it's been scaled to pass through the point of 0.5 just to make it easier to compare with the others. All right, so at this point in time, it would be good to pause the video to see if you can learn a decision tree for this data set. So we've been talking about the case of this vehicle at an intersection, or the self-driving vehicle at an intersection, based and trying to learn how to carve up the state space in order to make decisions based on two features, specifically the traffic light color and then the following distance. So the traffic light color can take on either red or green, and then the following distance is any continuous value, and then the vehicle decision, the output of the model is either to brake or cruise, so this kind of binary decision. So yeah, I'd recommend pausing the video now and finding out how you can figuring out what that decision tree would look like. So this would involve selecting a loss function, and then finding out that first feature, as well as that first threshold on which to split in order to minimize the loss after the split. Okay, hopefully you've taken a couple minutes now to try to work this out on your own. But now let's go through the solution. So the goal is to define that first root node That's the first step in growing our tree. And so let's consider the specific loss function of the Gini index. Let's select that. And yeah, that first root node uh, we have to consider splits on each of the features. So let's start with the splitting on the traffic light condition. So this one's easy because it can only take on two possible values, so we only have to consider one threshold essentially. So for the so let's consider first the red subspace. So in this case, the red. So we look at the red subspace and then identify the class labels inside there. So we have 1, 2, 3, 4 observations within the red subspace, and they're labeled break, 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 and cruise. So the empirical fraction of break within the red subspace is 0.75, and the empirical fraction within the red subspace for cruise is 0.25. So the Gini index is the empirical fraction times 1 minus the empirical fraction. So for the break, that would be 0.75 times 1 minus 0.75. And then the Gini index sums over all such classes. So then we would add in the Gini for the cruise as well. That would give us 0.1875 plus 0.1875. So a loss of 0.375 within the red subspace. But we also need to know the loss within the green subspace. And so let's go back and look at what's going on in the green. So green, we have 1, 2, 3, 4, 5, 6 observations within that subspace, and they're labeled break, 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 cruise, cruise, cruise. Okay, so that gives us a empirical fraction of 0.5 because we saw 3 within the green subspace. We saw 3 breaks, and then we saw 3 cruises. So the empirical fraction is 0.5 for each case. So that one's pretty easy. It's just 0.5 times 0.5 plus 0.5 times 0.5. So that's going to give us a loss of 0.5 within the green subspace. And then the total loss for this split is going to be a weighted sum of the loss within the red subspace and the green subspace. And they're going to be weighted by their respective sizes. So we saw four instances within the red subspace. So we multiply that by multiplier 0.375 times 4 over 10. And then within our green subspace, we multiply 0.5 times 6 over 10. So that's going to give us a total loss for this particular split of 0.45. Okay, so we know what it would be if we split on traffic light condition first. We can't do any better than this for this particular data set because that's literally the only thing we can do. There's only one possible threshold here. But now let's consider a split on the distance. So to save time, let's look at 20. Let's look at 20 meters as our threshold. So let's just consider this case first, and then we'll do let's consider splitting right here. So either less than 20 meters, less than or equal to 20 meters, or greater than 20 meters. Okay, so less than or equal to 20 meters. We've got 6 data points, and they're labeled break, 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 cruise. The empirical fraction of break is going to be 5 over 6, and the empirical fraction of cruise is going to be 1 over 6. All right, so yeah, break 5 over 6, and then cruise is going to be 1 over 6. So these are those empirical fractions. And then our Gini index, it's going to be 0.833 times 1 minus 0.833. And for the cruise, we've got that there. It's going to leave us as 2 times 0.1875 for a total loss within the less than or equal to 20 meters subspace of 0.278. And then for greater than 20 meters, let's take a look at that. So there's, for greater than 20 meters, there's 4 instances within that class, and they're labeled break, cruise, cruise, cruise. So the empirical fraction of break is going to be 1 over 4, and the empirical fraction of cruise is going to be 3 over 4. Right. So yeah, empirical fraction of break, 1 over 4.25, empirical fraction of cruise, 0.75. We can calculate the Gini index, exploit some similarity that we did within the looking at the red case. So that's going to be 0.375 again. And now our weighted loss for this split is going to be the weighted sum, or the total loss if we were to split on the distance with this threshold. We do a weighted sum of these individual losses, so 6 over 10 times 0.278, and then 4 over 10 times 0.375. And then we can add those two resulting values up, and that's going to give us a loss of 0.368. So this loss is less than the loss we could achieve splitting on the traffic light condition. So we absolutely know that we're going to be splitting on the distance instead, because we would achieve a lower loss after the split than we could with the traffic light condition. In practice, we would want to try out all other thresholds, because we don't know if we could do even better than this, but we've at least eliminated the idea that we should be splitting on the traffic light condition. Definitely splitting on the distance. What we're not sure of is whether 20 meters is the best possible threshold that we could do. But I think that's enough for you to get the idea that this is how learning a decision tree works. So yeah, we've talked about growing a decision tree. We went through an empirical example of identifying that next feature and threshold to look at. But we also have to establish some stopping criteria. So yeah, when do we stop growing the tree? This is essential to avoid overfitting and ensure that the tree is both efficient and interpretable. And so there's a few possible stopping criteria that you can consider. Once is to monitor and check for homogeneity within the leaves. So this means that the nodes or the leaves at the end of the tree contain samples that only belong to one class, in which case you know that further splitting, like you can't do any better with further splitting. Another possibility is to predefine some minimal improvement that you need in order to justify going deeper into the tree. So for example, if the reduction in the loss between the previous split and then the loss of the next split, if that falls below some threshold, some stopping threshold, then yeah, you would stop growing the tree there. Another possibility is that if your leaves are sparse, if each leaf or node has very few samples in it, as you partition the space more and more, there's going to be less samples because your subregions are getting smaller. And so you may end up with leaves that have very few training data examples inside of it. And this can be a concern because if you have really sparse leaves, that might not generalize well. And so a common stopping criteria is to enforce a minimum number of samples per leaf or node. And yeah, should have appeared in this bullet point here. There are some minimum number of samples per leaf or node. You could also predefine a certain depth, or maybe height, because we're talking about a tree. So maybe if the tree reaches a predefined maximum depth, like three nodes or four nodes, then you just stop growing the tree at that point. An extreme example is of this would be a decision stump in which you stop after figuring out the first threshold, the first feature and first threshold. So this would create a really fast but not very accurate tree. And finally, you could also just specify the stopping criteria based on the time taken by the algorithm to run. So yeah, if the tree is growing very slowly or taking too long to optimize, you could just stop it to save computation time. Uh, so there's also a method to do regularization over indecision trees. And so that's going to involve introducing a penalty for the number of leaves n sub v. So this is the number of leaves here. And then introducing a hyperparameter alpha to control the strength of this penalty relative to the loss in our that we've defined and been working with before. And so the idea would be then to minimize this whole expression. And so how this is done is to actually grow the tree fully up until that stopping criterion or just grow the tree fully, and then do pruning to shrink the tree back to find out when this full expression is minimized given your hyperparameter alpha. So for example, this tree would have four leaves. This tree here would have three, and this is the decision stump that would have just the two leaves. And so yeah, if you had a very, very large alpha, then you would be strongly penalizing the number of leaves, in which case you might end up with something like this. Whereas if you had a very small alpha, then that would favor very, very deep trees and would do very little pruning and favor accuracy. And so this alpha parameter can be selected using cross-validation, just like we did in regression. Okay, so that brings us to the end of this lecture on decision trees. So we'll now do a quick summary of what we covered and what you can expect to now be able to do now that we talked about this, went over this material. So yeah, we talked about the anatomy of the decision tree. We identified the components and structure that go into such a model. So things like describing trees in terms of the nodes, leaves, partitions or splits, as well as the threshold within those splits. We also went over a concrete numerical example for how we would go about learning a decision tree model by applying those recursive partitioning techniques, as well as a brute force search over the feature and threshold space. We also encountered three loss functions and some of their key differences. So we talked about the entropy, the Gini index, as well as the misclassification error, and they're all related to providing some notion of impurity within a subregion, or quantifying some level of impurity within that subregion. Um, we also talked about the specific contexts in which you might want to use a decision tree. Specifically, when you really need a like an interpretable model, when you want to be able to communicate what the model is going to output for any part of the feature space, where you want to know how it's going to generalize to situations that it hasn't seen before. And yeah, last but not least, we also talked about ways to improve robustness by regularizing over introducing regularization and hyperparameter tuning of alpha using cross validation to make sure that we haven't overfit to the data set. So yeah, we talked about what regularization looks like for decision trees, and it's a little bit different from what we've seen with regression. Okay, so that brings us to the end of this lecture. In lecture 11, we're going to be moving on to ensemble techniques, specifically bagging and boosting, which is going to allow us to turn a kind of weak classifier into a strong classifier by kind of putting lots of these weak models together. And so it's kind of related to what we talked about today with decision trees, where we could have that, where we could have like a decision stump that on its own is not very accurate at all. But maybe if we put lots of them together, maybe we would have a strong model. Okay, so we'll see you back here next time. Okay, thanks for your attention.